Oh yeah. So by the way, so I keep updating the lecture note at the overleaf. So please refer to the latest lecture note because I mean there were lots of typos and so on. Even this morning, I just keep updating all of the lots of typos. So so yeah, please refer to this latest one. Otherwise, lots of wrong informations at all in the previous previous notes. So even like a 10 minutes before, I just keep changing, correcting typos and so on. So you should refer to the latest lecture note if you want to. Yeah. Anyway, yeah. But anyway, so this lecture I always record, and also I just keep updating the lecture note in order for you guys to focus on the lectures, so that you can just, if you miss something, I mean, you can watch the video or you can just go look back to the lecture note. So the reason why I keep recording and also writing a lecture notes to in order for the, I wish the students focus on the what I said instead of like looking at something else. Anyway, so formal lecture is left, and then I plan to focus on high dimensional conformal field theory, and in particular today I'm going to talk about the representation of conformal algebra in arbitrary dimension in d is greater than 2. So, but recall that when we do the representation or minimum model, so we start with primary state in 2D. For instance, the 2D, you start with primary state, primary. And then you just consider one module L minus 2 or L minus 1 square level, sorry, L minus 1 H, and then L minus 1 square, and then what was that? And so on. So those are one module. So one module. And at some point, you encounter some singular vector, which is another by L, like this way, singular vector, and from there, you have a null state. All the descendant of this singular vector is a big unknown, and then these are. So now for this is a sub-representation of Virasoro algebra, and then to get the irreducible one, you have to get rid of this purple one. Anyway, so depending on the body of H, you encounter many singular vector, which can be, and the position of the singular vector can be found from the Katz-Shapovalov matrix or Katz determinant. So that's what we did in 2D. But for high dimension, it's not infinite dimensional. High dimensional, so this is the 2D conformal algebra is the Virasoro. But here you have this generator. Anyway, so J nu, so that's rotation. So just recap. P nu is the, what was that? Translation. Is special conformal transformation, D is dilatation. So those are generated of the high dimensional conformal algebra. And this one corresponding to Virasoro L minus 1, this one corresponds to L1, and this one corresponds to, roughly speaking, L0. Roughly speaking. Okay. Or roughly speaking. Or including the, I don't think, anthropomorphic one. and plus minus. And so roughly corresponding to, so P corresponding to L minus 1, and K corresponding to L plus 1. And then, of course, it's a finite dimensional Lie algebra rather than infinite dimensional. And then in high dimension, primary state is the again. So the whatever primary state, I don't remember what's my notation. Let's say H is equal to 0 or delta, whatever is okay, is equal to the primary. Okay, so that's the in high dimension. So now D is greater than 2. And to start with the primary state, we just ask lots of lowering operator, or like this. So those are your both like corresponding bubble module in high dimension. Now the question is, can you find a singular vector psi in this bubble module psi such that the k mu of psi is equal to 0 in the where psi is inside a bubble of delta, which is the p mu 1 in L, and then delta L is the natural number, or whatever C, like this. So that's a bone motion. So the same reasoning as before. So the psi is equal to 0 because psi is the descendant, right? Psi is descendant. So therefore, P mu is written in something like this. But P and mu is the k mu dagger. So therefore, if you act on the left side, so it's just k mu acts on the side, so which is equal to 0 because of this condition. So this is the so that is called singular vector. Okay. And again, the same reason as the 2D case. So if you ask lots of P mu, you get the infinite many node state. Yeah, it's the same reason here, node state, infinite many node states. So you just ask a P like a P many times, you get the again subrepresentation of conformal algebra. So to get the irreducible representation, you need to get rid of this focal. So the question is when? How do you find this singular vector in high dimensional conformal algebra? So that's the question I wanted to ask today. So that's the question. That's the first part of this lecture. Any question? Okay. So that's the first part of the goal. Okay. So in the primary state, so this is the primary state, is characterized by this way. So D is the denotation. And then at the end of the last lecture, as I mentioned, so this you have always have energy conservation, energy momentum conservation. So therefore, in CFD, there is a state operator correspondence. There is a T mu. So therefore, this equation motion is equivalent to P mu acts on T mu. So this is singular vector. So this means that Okay. In CFD. Of course, now I assume always CFD. So this is the state operator correspondence only works for CFD, not arbitrary QFT. So this is the operator or field of whatever you call it, a corresponding state. There's a one-to-one correspondence only for CFD. And the question is any like a systematic way of finding such a singular vector in the Bernoulli module. So to find, let's suppose here is a representation of SO. If it is a Minkowski SO, if it is a Euclidean SOD space, so let's consider this conformal algebra. So CFD, D-dimensional Euclidean CFD. So the output, the conformal algebra, is the SOD minus 1 comma 1. Sorry, I told you a D plus 1. Okay. And then, so this Bernoulli module. So this is Bernoulli module. I think I use different color. So this Bernoulli module is a Bernoulli module. Is the infinite dimensional representation of the SOD plus 1. Infinite, but it's in general this is not irreducible. As I mentioned, the singular vector occurs. Okay, so to find the irreducible representation, we need to find a singular vector. So the primary state. Let's consider primary state of rank L. Symmetric traceless tensor. I call it this one is the O. L1, not L1. My notation is sigma 1 dot sigma L. So this is the primary state with the L symmetric traceless tensor. So for instance, so T mu is the second. For instance, this one is the second symmetric traceless tensor. Okay. So as we know, T mu is equal to T mu. Okay. And also symmetric means like this one. Traceless means like this. So Lagrange symmetric traceless tensor is that the O sigma 1 dot sigma L is equal to O sigma 1 dot sigma J sigma I sigma L. So even if you swap these two, it's fine. Same operator. Sigma 1, sigma I, sigma J, sigma L. I hope my indices is visible. This is I. Okay, maybe it's better to use the other notation. M and I. Okay, so then here is I and N. So symmetric means that even if you arbitrary indices, even you swap, this means symmetric. And traceless is of course G sigma M sigma I O sigma is here. So if you take a contraction between any indices, you get Z. So that means traceless. And that's a property of the L rank L symmetric traceless. Let's consider such a tensor. Tensor, and this is primary. Primary means this property is satisfied. This property is satisfied. Okay. Let's consider such as. Okay, and then Yeah, so there's the operator and state operator corresponding. Okay, just I mean, if you have T mu, you have a second symmetry, and then you can have various the higher symmetries. So this the way today's the first one is that I just follow the Osborne section. I cited in my lecture note, so it should be okay. But anyway, so I hope my lecture note is enough to be understood. I mean, so this one is more detailed, more advanced actually. It's a Cambridge lecture note. So, I just follow the way they derive the singular vector. So to derive singular vectors, so we just have the construct something the state index free. So index free descendant. So I just want to construct index free. Index free means, I mean, since this Bernoulli module, you just apply lots of p mu. I mean, you have a lot of indices which show up in the Bernoulli module, but I just want to avoid that one. And then I just this time I have to be careful on I strictly follow my lecture note because the indices and so on are really complicated. I hope, and I have to write them very clearly. It's kind of complicated. So this is the primary field, rank L, symmetric choice tensor primary field, and a lot of p mu axon, p axon. So therefore this is descendant. But this t is a null vector. T mu is a null coordinate. So therefore t squared is equal to 0. We just knew the light cone vector or null coordinate. Okay, light cone vector. It's just it's not operator. It's just a vector. So therefore, if you take the as you know, so if you take the some contraction of indices, you get 0. We know you get 0. But if you take the contraction of the same indices, you get t squared. You get t squared. T squared means the t mu is equal to 0. So therefore, if you take a light cone vector, so this trace size condition automatically satisfied. So, okay. So therefore, this guy. So this one correspond rank K symmetric traceless so K means rank K is that K minus R is coming from here. K minus R T here, and also R T here. So in total, KT. Okay, the KT vector here. So therefore, essentially, you have a rank K tensor, and then traceless coming from the traces coming from T is the light cone, and then symmetric come from original construction. So that's the case. Okay, and of course we have a condition that so it's labeled by K and N and R. K is the around K, and N is the how many P square axon, and then R is the how many let's see. R is the K minus R and then L minus R axon. So, and then what is the conformal dimension? Oh. So this is I actually. Is the, in fact, original one, L plus K plus 2N plus 2R. Like this. So as you can easily see, so original, this primary field has a conformal dimension. This has conformal dimension. It's the outer. And you just need to count how many P axons. So here you have the K minus R P axonate, and this is plus 2N P axonate, and here you have L minus R P axonate. Okay? So therefore, if you sum them up, you get the L plus K plus 2N minus 2R. So that's the control dimension of this descendant. Okay. Tensor. Oh, and this is descendant. Okay. So because I'm in P axon. Fine. So example. So the example of when L. So if you start with T mu, then L is equal to 2, R is equal to 1, N equal to 0, and K equal to 1 case. If you consider such a case, we have the T mu, P mu, axon T mu. So that's a state. And the index free means that always these indices are contracted with something else. And then, for instance, the other thing is the L is equal to 2, R is equal to 2, N equal to 0, T rho, T mu, P rho, and T mu. So that's a descendant. We concept. Okay, so that's the case. So anyway, so you just act a P on this the primary field, some symmetric traceless tensor, which is primary, and then what? So you contract with T with the other indices. And to find the senior vector, so let's recall the conformal algebra, and in particular, so conformal algebra. I mean, we did a long time ago. For instance, conformal algebra is I. For instance, P mu, K mu is equal to 2 delta mu nu P plus 2 J mu nu. And so this kind of, these are, I think second lecture or some first lecture, second lecture, I already introduced this kind of conformal algebra. But if you use this conformal algebra, one can show the following. So this one I'm not going to derive. So it's a tedious one. P rho, T rho to the K. So this part is exactly this one. It's this one. Okay, and this one, if you use this one many times, what you get is as follows: 2k p rho t rho p nu like this. Like this thing. And also n. This one you get the whole n p squared n minus 1 minus I p mu j b mu plus p mu I d plus n minus d over 2. Like this. Note that here, so this one corresponding to this one. This one. Okay, and then something other thing what's left is of course the what's left is this guy. What's left is this guy, and then to find a singular vector, always you need to find the commutation ratio between these chunks. Sigma r plus 1 is the 2 times L minus R delta minus D minus R plus 1 T I don't think I have space, so you write right here. So these are some number, and then P sigma R plus 1 P sigma L. But now we have O mu sigma 1 sigma L minus 1. Okay. So it increase the the rank of the primary field. Just I hope let me check. Yep. That you can show by using conformal algebra. So this one it's really tedious, so let's accept this one. So this is the tedious calculation. So I don't want to derive this one by from the scratch, because I mean it's really takes a lot of time. So let's accept this one, and to see the how if you use this algebra is when K mu acts on this descendant. So what was that? If you act on this one, you get the following thing. Unfortunately, I have to write. Yeah, unfortunately, I have to write minus 4n and delta plus L plus n minus r. I mean that this one you don't need to write down everything. I mean because it's written in the lecture note. O L K n minus 1 n and r. Okay, like this way plus minus 2i k minus r delta plus k plus L plus 2n minus r minus 1 t mu O L k minus 1 n r t. Okay, and minus 4i n r t mu e O L and then minus 2i L minus r delta minus d minus r plus 1 and O mu L E K N R. And furthermore, the last time 4i and r O L mu K minus 1 R minus 1. Okay, so that's how K acts on this and descendant. How does K acts on descendant? Descendant constructed here. And the question is when this right hand side becomes 0. That is a singular vector. Okay. That is a singular vector.
Excuse me.
Yes.
The first that OP minus 1 or not.
Thank you very much.
R.
Thank you very much. N minus 1. And then this including mu is that you just go to higher rank. So increase the rank by 1 by adding this mu tensor. So that is the in here. In here, in mu here. Okay? Mu here. 2. So essentially mu here is essentially mu here. That's it. Okay, that's the definition of the. So now the question is when this right hand side becomes 0. The question. There are 3 patterns. Like a two-way of vanishing. When right hand side, there is 2 way of vanishing in the right hand side. So if you have this complicated formula, let's try to simplify it. What's the best way to simplify right hand side to be 0? Can you tell me? It's a huge formula, but if you are a physicist, you have to guess. What the first thing you should do is what? To make it 0. To make it 0 is the simplest way. What's the best way to do? First thing to do is what's the best way to make it 0? First thing to do is what? If I look at this formula, first thing I should set n equal to 0. I will set this n equal to 0. Okay. N equal to 0. If you set n equal to 0, you don't need to think about this term. So You don't need to think about this term. So no need to think about this term. And no need to think about this term. No need to think about this term. Because n equal to 0, n equal to 0, n equal to 0. Okay? What's left is these two. Okay? Then we need to impose these two terms is to become 0. Okay? And there are two ways of doing that. Okay, maybe I should set the n equal to 0 first. And two ways of doing that. First, you set the r is equal to L. So this term vanish. R equal to 0, R equal to L. Okay. And then the Conformal dimension, I call it I. Star means the Conformal dimension of the original primary field. Okay. Original primary field is the satisfy this condition. So R equal to L means that this term is 0. Okay. So to make it this term 0, this term needs to be 0. Okay. This term needs to be 0. But now we set the R equal to L, so therefore this term do not contribute. Okay. So therefore what you have is that the delta I is 1, where n like this. Okay, so that's the case. So I think what I should say is so this one should be k. So now n equal to 0 and L minus R is equal to 0. So therefore this should be 1 minus k. So that's 1 minus k. I don't know why I wrote like this. Just for do I need to? In the lecture note, I wrote like this way. This one is equal to 1 minus L minus m, where the m is equal to k minus L, which is the positive number. Like this way. I don't know why I wrote like this, but that's the same thing as a whole. And number 2 is that the second possibility, first you set k equal to r. R is equal to k. And then this term is equal to 0. So therefore, okay, like this way. And then k runs for 0, 1. Okay, that's it. Okay, anyway, so that's a way of constructing singular vector. And then this guy corresponding to following thing. So I call it O1, type 1, T. And okay, so I should use 1 and 2. I should use like this one. This one corresponding to T to the n. Like this. That's a state. And on the other hand, this second case corresponding to O2 of T, this one corresponding to the following. Like this. Okay. So that's a singular vector inside a Graham motion. Okay, and then here this compound dimension of upper one, this one, this S means singular vector is the star I plus M, and the spin is the L plus delta I S minus delta I star. Okay, so that's a spin you will get. So this means the L plus N. Like this. On the other hand, L star. I mean, okay, L is okay. On the other hand, here the bottom one is the I2. Singular is the I minus K plus L. Okay, that's the compound dimension because I mean you just act the P in L minus K times. Whereas in the here uppercase you just act the P in M times. And the star means original the compound dimension, original parameter. And then the spin of singular vector is L E minus L minus K. Okay. So therefore, this is equal to K. So this is equal to K. Okay, so that's the spin of the Lisa. Okay, so that's the representation singular. Then let's examine what this means. Okay. So let's examine what this descendant means. Singular vector. These are singular vector. So these are singular vector. In the flow module. Okay. And let's examine what the physical meaning of this singular vector. So to have the okay, let's do one by one. So let's look at number one case. Okay. So we'll consider that this usually so unitary CFT So this one only occurs, so we will say L equal to 0 and M equal to 1. Okay. So which means that the this can happen. In unitary sieve, this thing is going to have only. So this means that this operator is spin 0, which means scalar. And this is scalar primary. Scalar primary, and M equal to 1 means the P dot T acts on it. Okay. Then in unitary CFT, this is means singular vector means this is equal to 0. Okay. This is equal to 0. So this means that the operator O is the identity operator. So this means that this means that exactly the partial new operator is equal to 0, which means that this is identity operator. Okay. Because I mean we already knew that the P mu operator, and then you just take the norm of it. If you take a norm of it, you have a K mu of operator. And you use this conformal algebra. This is 2R times the, okay, so this is the P mu. The scalar operator 2R times O. And this is equal to 2 times delta mu delta O and O. So here O is the scalar because L equal to 0. So there is no spin. There is no spin. And so therefore J acts on O as trivial. Okay. It's a scalar operator, this is rotation. The scalar operator acts trivially in the rotation. Therefore, what's left is this one. For unitary CFT, this is equal to greater than 0. And then when P acts on O is equal to 0 means delta. Delta has to be 0. Okay. Delta has to be 0. So this P mu acts on operator is equal to 0 means delta is equal to 0, which means just a vacuum or identity operator. O is identity operator. So that's the number one case. When L equal to this is L equal to 0 case, and then there is no such a descendants appear for unitary CFT except L equal to 0. Requires some care, but I'm going to omit this proof. You can accept at this moment as a fact. So number one case is very special. So this descendant is a very special one. It's actually not descendant. It's a primary state because it's just identity operator or it's just vacuum. So this number one case, so it's very special. And number two is the really generic singular vector. Let's look at the following case when L is equal to K plus 1. The special case. So if you look at the L plus 1 means that the only one P acts on operator O. Okay. You understand? K plus 1 is equal to L means only one P acts on O becomes singular vector. And in unitary CFT, so singular vector is the, so which means that the P mu, P whatever, sigma L acts on operator, or sigma 1 acts on sigma 1, sigma L is equal to 0. So, okay, so this means, okay, so this corresponding to the conservation current, sigma 1, J sigma 1, sigma L is equal to 0. So this is the rank L, rank L symmetric traceless conserved current. Okay, and its conformal dimension delta is really restrictive. Okay, so just a moment. So did I erase? Okay, so now, so as I mentioned, delta star should be equal to D plus K minus 1. And plug that one into here. What you find is that this one is equal to D plus L minus 1. Okay. D plus D, sorry. There's something strange. There's something strange here. Do I make a mistake? Yeah. Yeah, it's okay. It's okay. Sorry. So it's okay. So this is a D minus. So therefore this J has a delta D plus L minus 2 actually of conformal dimension. And this is it. So this is the dimension of the descendant or singular vector. And since it's only one P acts on the primary field, it just increased by one dimension, by one. Okay? So therefore, the primary field J, primary operator J, should have a D plus L minus 2 conformal dimension. And if this P acts on primary field, the conformal dimension becomes D plus L minus 1. Okay? That's what I mean. Okay? Fine. So that's the what's really happening. And then so in other words, the if primary operator of dimension delta is not D plus L minus 2, that's not the case, then it is not conserved. Okay. Higher tensor operator is not conserved. And let's look at the example. Our favorite example is always the spin is equal to 2. Okay, spin equal to 2, and then in that case, J mu nu, okay, has the conformal dimension is equal to D. Okay, J mu nu has a conformal dimension D, and it's conserved. It's conserved like this way, and it's a spin 2 symmetric traceless tensor, and the conformal dimension D means that the J mu nu is in fact the stress energy tensor. Okay, that's the case. Okay. So now for once we set L is equal to k plus 1 case for this singular vector, that will give you the conservation of the current in a CFT. In a CFT. So what if the R is greater than k plus 1? So this means that the lots of sigma, what's the condition? K plus 1. Okay, so that's the case. So this means that this guy, so for instance, L is equal to k plus 2 case. In this case, we have the following operator. Okay, like this. That's so therefore, this operator is often called a partially conserved. The partially conserved current. Okay, so that's the case. So the corresponding singular vector is the singular vector. You start with such an operator which satisfies this condition. You will encounter singular vector in the bound module. In the bound module in type 2. So this is EG. Okay, so those are two types of singular vector you will encounter in bound module. But however, you will see lot more interesting things happening in there's type 3. So there's number 1, number 2, and number 3 I will explain. In higher dimensional completely singular vector becomes like this way. Okay, so the operator we are looking at is, so let me write it again. I mean, it's already written many times. So, but the operator, the descendant we're looking at is this one. K, N, R, O, T, and minus I to the some power. I'm not going to write down again. P rho, T rho, K minus R, T squared, N, T sigma 1. T sigma k and P sigma k plus 1, T sigma L, and the operator sigma 1, sigma L. Like this. So this is the descendant we are looking at. And this has a conformal dimension. So this conformal dimension of this operator K N R T is equal to del plus L plus K plus 2N minus 2R. Okay? And then a conformal dimension. So therefore, if you just consider the two operators, so operator L, K, n 0 plus my notation is the R, and R of T has the same spin as the, and if you compare with the O, L, so this has the same conformal dimension. Okay. So if you R equal to 0, R equal to 0. Okay. Sorry, I think I told you wrong. It should be R. So this should be R. Sorry. Sorry about R. When R equal to 0, it's so these two has the same. The spin is this is the rank K symmetric tensor, rank K symmetric tensor, and the conformal dimension is the conformal dimension of this descendant is delta star plus the L what was that? Plus K plus 2 and 0. So that those are the conformal dimension. It both have the same spin and the same. So where R is the 0, 1, 2, 3. You can just have the arbitrary, not arbitrary, till L. Okay. Till L plus 1, L minus 1. Because if you set R is equal to L, it becomes it becomes the, oh, it's okay. I think it's totally fine to have L till L. So they have the same spin, and same conformal dimension. Okay. So therefore, maybe you can consider the linear combination of these descendant to construct a descendant. Singular vector. So we can construct. In fact, we can construct singular vector by a linear combination of these states. So the previously I already raised, I wrote the K mu acts on this operator. I think I can. So previously I wrote a big formula, K mu acts on this OL, was a K and R of T, and it's how many lines I had? I think 5 lines I wrote. But this is only the K mu acts on only one descendant constructed like this. But in addition to that, one can consider a linear combination of such a descendant. Okay, and how does K act on linear? And in fact, the following thing is the number 3 case will appear as follows. Number 3 singular vector is as Yeah, so you can consider such a linear combination, and this is to become singular vector. This analysis, the K-mu analysis for 3, it's tedious calculation. I'm going to omit. So it becomes like this. So this one is the Pochhammer symbol. So you know Pochhammer symbol. So this is Pochhammer symbol. So this is the x plus 1, x plus 2, over x plus r minus 1. Okay, so that's the product. So essentially this is just number. Small d's are always dimension of the spacetime. And then if you take the Pochhammer, and this is another by K. Fine. And then conformal dimension of this guy. Okay. This delta 3 star plus 2m. Sorry, what is 2m? It should be related to n0. Yeah. I need to mention one thing. Yeah. Original primary field. So this is not true. This is not true. Original primary field should satisfy the following condition. When delta star 3 is equal to d over 2 minus m, and the k is equal to l. K is equal to l, and then m is equal to l plus n minus r. Okay. Then K mu acts on all 3 of T is equal to 0. You can show that by using conformal algebra. So there's something strange. Sorry. I see. I see. So yeah. So K is equal to L. Okay, K is equal to L. Come from so this has to be L. So which means this has to be L. So here this part, it has to be L. So that's what it means. And then L plus n minus r. L plus n minus r. L minus r is this part. Okay. Plus n has to be equal to n. Okay. So that's the condition. So the number of this p And number of this p square, if you add them up, it has to be equal to this number n. This number n should be equal. Okay. If this condition is satisfied, so the Camus annihilates this linear combination. So therefore this becomes singular vector. So that's what. And this has conformal dimension. Singular vector is the number 3 plus 2m. Okay. So can you show this one? So this one is equal to, so it has to be 2L. Yeah, it should be okay. Here, you just take R is the same number, so this should be equal to, when you set R equal to 0, this is equal to delta star plus 2 times L plus 2 times M, which is equal to this. And this is equal to delta star is 2L plus 3M under this condition. It should be okay. And then L number 3, S is equal to L. The spin does not change from original. Okay. So let's try to understand what this descendant means. Let's try to understand what this singular vector means. Let's set the simplest example. Let's set the simplest example, k equal to 0 and then L equal to 0. Okay. In that case, delta star is equal to d minus 2 minus m. Okay. I don't think there's R here. I don't need this R here, to be honest. Because my R can be run from 0 to L. 0 to L, so sorry. So there must be typo in my lecture note. Yeah, R can be 0 to L, so we can set the M is equal to R equal to be 0. So sorry. So in that case, when L is equal to K equal to 0, this is the conformal dimension. Okay. And then this singular vector, K equal to 0, R equal to 0, L equal to 0 means that this singular vector, or all three, of P is equal to P square M factor of O. Okay. So L equal to 0 means it is scalar parameter. So L equal to 0 means that this one is scalar parameter. And then the p square to the n axiom O is equal to 0. So this is equal to singular vector means 0. This is a singular vector. Okay. Okay. And the unitary CFT. Okay. In unitary CFTs. Okay. Unitary CFT. So this only occurs n equal to 1 case, which means that p square to the n sorry. N equal to one case. Occurs n equal to one case, which means that the p square action operator is equal to 0. This is equivalent to Gordon equation. And then this has the conformation delta is called d over 2 minus 1. Okay. So this means that this operator O is corresponding to this operator O corresponding to just a prescalar of the ddx 1/2 dou mu phi in the flat background. So this is the S is equal to 1, and then operator O is just the phi corresponding to the state operator correspondence O. Okay. And then this is the Klein-Gordon equation. So this is consistent. I mean, here always phi has the conformation d over 2 minus 1. D over 2 minus 1. Okay, so when you set n equal to one case, exactly conformation corresponding to conformation of the prescale. Okay, so that's the analysis of the singular vector tells us. So option is that just considering the conformal algebra, representation conformal algebra, we just encounter the three cases of the singular vectors. So number one is in fact just identity operator. It's just identity operator. It's just a unitary CFD. Unitary and spin zero case. Spin zero case. N equal to 0 means spin 0. It's identity operator. Spin 0. Unitary spin. And this way is essentially you get the current conservation. Essentially, current conservation or its generalization. Number three is essentially the unitary CFT. This occurs the p square, the Klein-Gordon equation. It's just Klein-Gordon equation. You encounter when L is equal to 0 case. When L equal to 0. Okay. So if you just considering the representation of conformal algebra, one can encounter this kind of like a conservation role, equation motion, and then the primary field that corresponds back in. So, okay, so that's the analysis of conformal algebra, representation of conformal algebra in high dimension. Okay, let's take a break for 10 or 15 minutes. And if you have a question, just let me know. Yeah, so let's take a break. 哎呀，
那大家都会。
So, by the way, next semester I'm going to teach statistical mechanics in 2 for graduate students. If you have any suggestion, this is the first time to teach statistical mechanics. So, if you have any suggestion, please let me know. So, this statistical mechanics 2, what are supposed to be covered? What kind of material is supposed to be covered? It's for graduate course, right? And it's a mandatory. It's called 必须. It's mandatory to take it. Yes. So if you contract with the original one, and then with this P, you will lose the. I mean, it's similar to partial mean, T median. This is P1. So if you contract with the indices use original one, so this means that if you consider this one, it has a spin R. Spin R. And then this will create a K minus R. So in total it becomes K. Spin K. Okay, shall we resume? But I just want to have something to drink. But anyway, sorry, maybe it's better to have something to drink. Otherwise, my voice may. 5 more minutes. 5 more minutes. I will buy something to drink. It's already. Okay, let's get started. Okay. So those descendants on senior vector will play important role when we call the conformal block and so on. But just leave it as it is and then think about some unitarity value. Okay, unitarity. So closely related to this senior vector in the one module, one can consider so-called unitarity bound in CFT. So unitarity mention of any state, Hilbert space in the any state, then the norm has to be positive dimension. Equality only for the vacuum state. That's unitarity. And this will tell the following thing. So as I mentioned that this P nu O, so this one I already showed many times. And if it is a scalar field, if it is a scalar, this one is the like this way. So therefore, unitarity will tell you that any scalar conformal dimension needs to be like this, and like this way, and then equality form. So equality form. When O is identity operator. Okay. It's identity operator. And one can say something much more than that if you consider a level 2 inner product. So this is level 1. So level 1. So if you consider level 2, you can consider following inner product P sigma P rho O P nu O, and then you do the conformal algebra. Okay. Sigma K rho P nu O. Actually, it's the opposite. Actually, rho sigma. And this one, after the conformal algebra, you get the following. Like this way, and then delta sigma rho delta mu nu, and then inner product of all. Like this. Okay. So that's the level 2 inner product you get. Question is, what can you tell you from here? Okay. So to tell something important, let's contract with the delta mu nu. If you contract with delta mu nu with this one, sorry, I think, am I correct? Yeah, I think it should be okay. If you contract with delta mu, you get the full delta, delta plus 1 times 2 delta sigma rho overall factor minus d delta sigma rho. Like this. Okay. This has to be positive or non-negative. Okay. So this means that this part is non-negative, means delta is greater than or equal to 1/2 d minus 2. Okay. So from level 2, one can say but more strict condition than level 1. Sorry. Of course, here I assume. So this one only true for O is the primary. O is the scalar primary. So this is assumption. So this is assumption. In here. Okay. So therefore, so if you use conformal algebra, one can just say that the conformal dimension of the scalar primary is bounded by d minus 2 over 2. It's 1/2 of d minus 2. Okay. And you may think if you go to the if you go to higher level, like a level 3 and level 4, like for instance, if you consider something like condition PPP or PPP O is the greater than 0. Can you say more like say stronger condition? Or delta? And then it's already proven this is not the case. This is not the case. This is not the case. It doesn't say anything more than level 2. And from conformal, this is the unitary bound. So for scalar parameter. Okay, that's the key. When D is greater than 2. Okay. Fine. And we can do something a bit more than that. So this is scalar field. So how about the rank L? Okay, rank L, symmetric, traceless tensor. Traceless tensor. Primary field. So the one I showed is O, sigma 1, and sigma L. Here you can do the same consideration as we did here. So the P nu operator, sigma 1, sigma L, K nu mu, P mu. And this is 2I, 2I times operator of sigma 1 to sigma L, and then down mu nu, J mu, and that operator sigma 1 plus sigma L. Okay, so that's the and then you can take the contraction with the I times J mu nu. Okay, if you take I times J mu nu, it's this one, and J mu mu on the acts on operator sigma 1 just received L of this O, the spin. This J mu mu trace part is just only take the spin condition, which I think tell you just something strange. It should be okay. And then J mu nu. So this one acts on this symmetric operator, which acts on L plus D minus 2. This is a Casimir operator. Plus Casimir operator. Okay. From there, we'll get the delta minus L plus D minus 2 is greater than or equal to 0. So this is greater than 0. And from there, delta has to be L plus D minus 2. For rank L symmetric traceless tensor, the conformal dimension needs to satisfy with this bound. Okay. So that's the So in the case of the d equal to 4, d equal to 4, we know that the how to say j mu nu, j square is equal to acts on whatever l. Okay, maybe I think this notation is more familiar. L plus 2 ish. So this condition. So this is the Kodakasmi of this is spin how to say rotational operator L squared is L plus L plus 2 when d equal to 4. So for after dimension j square will give you the this kind of Kodakasmi L times L plus b minus 2. That will condition will give you the unitarity bound for rank L symmetric traceless tensor prime ratio. Okay. So that's the okay. Okay, so that's the case. And then okay, so also we can do the symmetric traceless projection. Symmetric traceless projection for this one. If I do symmetric traceless projection, what's that? Let me think. Okay, so if you do a symmetric traceless projection on this condition, let's do that. So if you do the symmetric traceless condition, so for instance, so if you take symmetric traceless projection at all, if you consider this kind of O, and the symmetric traceless projection is as follows. Is still like this P mu minus delta mu nu divided by d P squared acts on O. Okay. So if you take contraction on mu and nu, so it's a symmetric and traceless means that if you take contraction mu and nu, this is equal to 0. You can see this is equal to 0. So the output is traceless. If you contract with the delta mu nu, this will give you 0. Okay. So if you do that, the same analysis on this one, so this time it drops. This time it will drop because I mean here it's not traceless, right? If you take a trace contract with delta mu nu, this time is no longer 0. Okay. So therefore, if you consider the following or whatever, P. Okay, let's this tensor is the let's go S mu nu. Okay. S mu nu. Oh. S mu nu. S rho sigma. S mu nu. Oh. Is greater than 0. So this will tell you that the delta times delta plus 1 is equal to greater than 0. So this condition will. So you just get rid of this part and only look at that this part is greater than. And in fact, if you look at this one closely, you will see that the case delta is -1, so it's non-unitary. But it becomes 0 norm. It becomes 0 norm, so this state becomes 0 norm. And in fact, this is consistent with what we consider in number 1. Yes, number 1 case. Say, so here we consider scalar field, so the alpha L is equal to 0. So number 1, set the L equal to 0. And then the M equal to 2. When M equal to 2, we have P dot T squared on O. It becomes this O1 of P, which is singular. Okay, it's a null state. Okay, null state. And this is exactly consistent with the analysis of this. So singular vector here corresponding to this S mu O becomes the 0 norm. So when delta is equal to -1 case, so the inner product becomes 0. And if you look at the here, delta star L equal to 0 and M equal to 2 case, so the conformation. So from here, we mention delta I star is equal to -1. And delta star, the primary state scalar field is delta star is for -1 case. If P traceless symmetric tensor acts on O, it becomes singular vector. Okay, singular vector. This is exactly the same conclusion what we use by just taking just norm here. Fine. Okay, so that's another thing. And then another important thing is that this unitarity bound has another meaning. So when you consider number 2 case, so this del mu, J mu, nu, okay, is equal to 0. So this is the rank L symmetric traceless tensor. That's conserved current. And this has delta should be delta D plus L minus 2. We already derived this from number 2 condition. So we just set that K is equal to, so L is equal to K plus 1. In number 2 case, we obtain this, rank L symmetric traces conserved current condition coming from this singular vector. Okay? And this exactly saturates this bound. This exactly saturates this bound of this unitarity bound. Okay. And then, so to get this bound, we take P acts on O and take inner product, right? P acts on. Okay, I see. I think I made a mistake. This is not correct way of taking. Yeah, anyways, so P acts on O and take a norm to get this unitarity bound. And when this is saturated, this norm is equal to 0. This is exactly corresponding to this current conservation. P acts on this state is equal to 0, this state is equal to 0. And in fact, so in that case, I think most likely what I need to do is take a contraction with like this way, sigma 1, like this way. That's the most natural thing to do. And then, yeah. Yeah, this is prime, tilde, sigma, sigma 1. And then here, sigma 1 tilde, sigma 1, like this. But anyway, so if you do the same analysis, you should get the same conclusion. Dot is bounded by L plus D minus 2. When it's saturated, this state will vanish. This is exactly corresponding to current conservation here. Current conservation. Okay, so that's the relation between singular vector in the conformal algebra and then the unitarity bound. Any question at this moment? Okay, if not, I think I will move on to operator products expansion. Okay. So let's take operator OP in high dimension, in D greater than 2. Okay, so let's consider the following thing. So operator product expansion is again, so if there is an operator of I of 0, and then there is some operator of j of x, and so which approach to the original, or the operator at the origin, and what's going to happen in the net effect. Net effect is become how it looks like from outside. And I didn't know this OPE is the concept of coming from Ken Wilson. Actually, Ken Wilson is a brilliant physicist. Wilson. I didn't know that actually before I prepared this lecture. Okay. Okay. So let's consider the following thing. So OPE is the OI of X, and then OJ. Oh, sorry, I think it's opposite. So my notation OJ and OI. Okay. Of 0, this can be written as follows. OK is the primary, andCijk, and X, and also there's some derivative X on it. So this is the operator products expansion. So here, so all the state is coming from, so as I mentioned, all the state is coming from primary operator K and its descendant. So this one module is coming from. So therefore, if you have some of primary and if you incorporate this derivative derivative acts on the operator. Here, it just means that it just constructed the linear combination of all the possible Hilbert space you consider from motion. Okay. However, one can say something much more than that. If you consider the 2-point function and 3-point function. So the constraint on OPE of the primary field from 2-point and 3-point function. So one can consider this constraints one can consider. Okay, so for instance, if you consider the 3-point function, so all are primary field, okay? All are primary field. So all primary fields 3-point function. So then we can take the OPE between these two. OPE. If you take OPE, what you get as follows. Sum of, just plug that one into here. Okay, is a primary sorry. My brain is not working. So Cijk and xip new acts on OL of Z and OK of Z. That's what you get. However, we know this 2-point function only non-vanishing when the OL and the OK are the same conformal dimension, same operator. Okay. Okay, so that project, the project OK to OL, so which means that the CIJL acts on XIP new, and then OL on C, and OL on C. Okay. So that's what 2-point function tells us. Okay. And however, so we know this. So this one will take the form at the one C 2 times conformal dimension delta. Okay, conformal dimension delta. This one we already know take the form that like a C minus X delta L plus delta I minus delta J, and then here X delta I plus delta J minus delta L, and here in C you have delta L plus delta J minus delta I. So like this. So then Cijk. Okay. So this is structure constant. Okay. So therefore, so here, if you compare between left-hand side and right-hand side, you can say something about this. What's this OP quotient? If you compare between these two, one can say something about this OP quotient. But moreover, so this one should take the form Cijk times some function, which I call C, X, and I times. And this CIJK, so do not confuse, this one is some function in x and then p, it's a derivative. This CIJK is a structure constant of the three-form function. Okay? So therefore, this function, CIJK function, can be written by structure constant times some function, some scalar function. I will say scalar. So it's which is independent of IJK. And if you compare between these two, one can determine in this structure constant order by order. So let's do this exercise in the simplest example. Suppose the simplest simplification. Since our brain is not smart enough, so it's better to consider, at least my brain is not smart enough, it's better to simplify the problem. Let's consider a conformal dimension of this primary field. Take the two of them primary field here. Two primary field has the same conformal dimension, small delta, and this has a capital delta. So that's the simplest example. Then if you compare between these two, structure constant cancel. So structure constant cancel. And then if you compare between these two, substitute this one, what you get as follows. So that's that. Okay. And then suppose x and z are real variable. So suppose x and z are real variable, so we can get rid of this absolute value. Okay, we can get rid of absolute value, and you just compare order by order by tail expansion. Okay, and then this can be done as follows. So this one is equal to 1 over z to delta, okay? And 1 plus delta x mean, z mean, z square, plus lots of things going on. Sorry, I think oh yeah. So I missed one thing. So x to delta minus delta to delta, small delta minus, and then z times to delta, and then which, and you just do the tail expansion in terms for this one, and and this one is equal to the following thing. So the x to delta, whatever, to delta minus delta, 1 plus 1/2 x mean, delta mean. I mean, this is the, I mean, and 8 times tau. So that's the we get. So therefore, so if you do the Taylor expansion of the 1 over z minus x in terms of x, like this way, and the right hand side, if you compare between these two, one can determine what kind of differential operator you should have, and what kind of function x you should have, compare between these two. That's how you determine this structure constant C, information C. Any questions at this moment? Okay. And actually, I want to write down the fourth term too, actually. So if you compare the fourth term, it's something like this one. Like this. So those were the structure constant you read. So what's the meaning of the structure constant? Let's examine some structure constant, the meaning of structure constant. So first of all, if you look at the third term, this is divergent. Out. The output is equal to -1. So if you substitute that equal to -1, numerator, denominator becomes 0. So therefore, this becomes divergent. But this sounds problematic. However, we already knew that from above analysis, in number one case, when L is equal to 0 and M equal to 2, then the outer star I is equal to -1. This is exactly the condition you will encounter here. So this term is divergent. Okay. However, we already knew that the symmetric tensor, second derivative of symmetric traceless p mu pt square acts on this operator O is a singular vector. And this is exactly what happens. So these two traceless symmetric derivative acts on this operator OK. Acts on operator OK, it becomes singular vector. So therefore, even though this is divergent, this operator here becomes singular vector. So therefore, you can get rid of it. So therefore, you don't need to worry. So therefore, if you look at the OP expansion, and then each term has a physical name. The same thing happens here. Delta equal to -1 case, you have a second derivative here, but that is becomes singular vector. And here, how about here? Delta. So we will encounter what if delta is d over 2 minus 1. What's this? When did you encounter this number? So this number has two meanings. Huh? Should I repeat again? Good, free scale. So this is a free scalar. Conformal dimension. Okay, conformal dimension. If this is the case, this term is divergent. But here, you have a Craig-Gordon operator. So therefore, delta phi is equal to 0. So box phi is equal to 0. So this one is already obtained from the I already forgot. Number three condition. Another meaning is that this one half v minus 2 saturates the bound of the unitarity bound. Okay. Another meaning, so this one saturates the bound. Okay. And to obtain the bound, what we did is that the PP axial operator is bounded by like this. Okay. And the bound that saturates the conformal equality only appear when this becomes 0 norm. Okay. If this is 0 norm featuring singular vector, so which exactly is two derivative appear on here. So therefore, if you do the OP expansion, it will give you some information when does new vector appear, when does the equation motion appear, when does current conservation appear, and so on. So therefore, so in CFD, okay, so all those analysis, so today we did a very heavy analysis. Unfortunately, I have 15 minutes, and then I don't want to go. I don't want to rush. But today's message is as follows. So we study the main message to here of today. Today we study representation of conformal algebra, and then find the singular vector. Find a singular vector. When singular vector. Here we don't use, so we only assume the theory is conformal. And we don't use any Lagrangian. We don't use anything. We just have a conformal algebra. Okay. Then, but however, this will tell you that let's say current conservation, and also unitarity bound. And then also current and also equation motion of the free scale. So now in CFT, so we just only study the algebra representation of conformal algebra, but even that one is give you some very important information of the theory. And furthermore, conformal symmetry determines the OP coefficient of the primary field, scalar primary field. So that's what we did around here is Cx minus. So OP coefficient is this Cx delta T or IP. Okay, Cx Cij. And this expansion OP quotient also tell you about heurispace information, detailed information about heurispace. And because state operator correspondence, and then operator spectrum. That's I wanted to convey today. So here, so we just did an OP expansion, but each coefficient has some meaning. Okay, some meaning. So one is this one is when the conformal dimension saturates the bound of the unitarity. This will give the norm become 0. So it's a singular vector. So therefore you have to get rid of from the heurispace. And also the same thing here. Even though delta is equal to -1 is non-unitary, you can consider such a primary state, but you encounter the singular vector in that case at the second symmetric traceless derivative axiom. That's the yes. And then so this analysis can be just I don't think. Let me write down the final expression. So this analysis simplification is delta I is equal to delta J is equal to small delta. So this is simplification we take. But we can just consider the generic case. Now I can erase this number 1, number 2 condition. Okay, so so delta I, I delta J and delta L are distinct. Oh, okay. Delta L is the OP quotient C X like this way. It's something like this one. It's really, so this is the formula obtained by any Osmo? Who they are? Let me check. Yeah, Mark. It's hard to. McAvity, okay. McAvity and also. So relatively recent. Oh, but I think before you guys are born. I was already born. But you guys are not born. Okay, so relatively recent, and this expression is called cross-form expression for 0, 1, d alpha a plus -1, 1 minus a minus 1, sum of n equal to 0 and infinity, minus 1/4 x squared, alpha minus alpha, box to the n. Okay, so that's the cross-form expression. Okay, so that's the Here it's a first derivative, a second derivative, and second derivative with like a trace part, and these are It just can be obtained by just integrand of this expression, and then here you need to do the tail expansion and just expand in alpha. Yeah, expand in alpha, and then just do the integration. So that's sorry, I think I have to mention various convention. Delta 1, 2, so sorry. A plus minus is equal to 1/2 delta plus minus delta 1 minus delta 2. And then delta, this is conformal dimension of the OK of E. So here I consider the following thing: OI of X, or J of 0, and the Cij of sum of K, primary Cij and the Cx axon derivative, and the OK of or X, and then sorry, not X. X is also okay, Z and Z. Okay, so that's the. Okay, so that's the. This is the derivative with respect to Z. Like this. And this, the delta up here is a conformal dimension of OK. Okay, so then you can have this kind of expression, cross-form expression. So that is the the constraint coming from just it's exactly what we did in I already erased. So just compare between 3-point function, 2-point function, and they use the conformal symmetry. One can obtain this. It's a kind of milestone. It's very beautiful. And then we can just do the something. Then, if you only look at n, rank n, symmetric, tensor symmetric differential operator. So we will have the following expression, essentially gamma function of delta plus delta 1/2. No. 1/2 plus m delta gamma delta plus delta 1/2. Okay. And this has a pole at the delta is equal to -1, -2, minus n plus 1. And this is exactly -1 appearing here, that appearing here is exactly the same reason as the I already erased. So this is number 1. So at all those places, you have the singular vector. At the when this singular vector occur when this symmetric differential operator rank n acts on this primary state with this negative. That's exactly what happens. Also, there's a pole. If you closely look at this formula, so the form delta is equal to d over 2 minus m minus 1 by p. So this also has a pole out. And also pole at this one. And this pole also indicates that when it acts, the rank n symmetric differential operator This will produce the null state or singular vector, null descendant. Okay. And then this physical meaning of this pole will be explained in subsequent lecture. And I don't know what to do. I think it's a good place to stop. 因为时间差不多了。Okay, so let's stop. Any question? This one? So because of this one, Jump function.
It seems that one is 1.
Is it the case? Jump 1 is 0, isn't it? No?
Comma is it doesn't matter what size.
Jump 1 is 1. Okay, so then most likely this is -2. Okay, maybe that's the case. Yeah, actually, so this pole is coming from here. Here, this pole coming from here. I didn't explain. So this pole is coming from when this part becomes 0. So that will also give you the information on the when this if the primary state with compound dimension here when the operator has the null descendant. Okay. Okay. Let's stop here, and then if you have a question, just tell me.